So this session is about coding and testing and various aspects of these problems. And I think testing and coding, especially local testing and coding, came to prominence as a key ingredient in the PCP, in the proof of the PCP theorem. And since then, maybe also before then, testing and correcting objects locally, given only local access, really is a foundational issue in theoretical computer science. And we have 4 papers in this session talking about various aspects of testing, decoding, correcting, both motivated directly by the PCP theorem and also more broadly about testing objects. So just briefly, when we talk about local testing in the coding theory setting, we have a tester that's given oracle access to a received word and wants, just using a few local queries, to know whether it's close to a word in the code. More broadly, when we're not just talking about coding theory, we can talk about any object, given, say, local access to a graph, trying to determine whether the graph has a certain property, whether it's close to a certain set, not just a code. So that's for testing, and then we also have local decoding and local correcting. So local decoding is the problem. Given a noisy received code word without too much noise, try to recover, using only local access, try to recover a symbol of the message. Local correction, similarly, we have a noisy code word with some bound on the noise, and now we want to recover symbols not of the message, but of the code word itself. So remove the noise from an arbitrary, possibly noisy symbol of the code word. With all of these in mind, 4 papers in the session today. The first paper about relaxed locally correctable codes talks about a relaxation to local correction where we don't require necessarily, we're not required to always recover the correct symbol of the code word if there's been a bounded amount of noise, but we're also allowed to fail. So the corrector is allowed to say, hold on, there has been some corruption in this code word, I don't know the answer, and output an error symbol. It's not allowed to output an incorrect symbol, but it's allowed to say, I fail. So it's a relaxation to the definition of locally correctable codes. And in this paper, Gur, Ramnarayan, and another Rothblum show under this relaxation exponential improvements to the parameters, talking about query complexity and rate of the code, exponential improvement for what was known for strict local correction. And their construction, these improvements use PCPs to construct these relaxed locally correctable codes. Prior work showed how to use PCPs, strong PCPs, to construct strong locally correctable codes. This paper shows relaxed variants of PCPs and how they can be used to construct relaxed locally correctable codes with improved parameters. I think we'll hear about a new composition theorem that they show. And looking at the reviews, reviews said this was a technical tour de force. The second paper about local decoding and testing polynomials over grids by Srinivasan and Sudan looks at variants of the Reed-Muller, the celebrated seminal Reed-Muller code. In the Reed-Muller code, code words are low-degree multivariate polynomials of a bounded degree over a field, and they're evaluated. In the Reed-Muller code, we evaluate them over the entire cube, f to the m. In general, we could talk about evaluating them over a subset of the field, so s to the m for some subset of the field f. And you would think that everything that needs to be known about Reed-Muller codes has been asked and has been studied, and hopefully we know everything we need to know, but in fact this isn't the case. The case of a general evaluating the polynomial over a general subset of f is wide open. Only recently do we have results for non-local unique decoding. And this is the first paper on local testing and decoding for general subsets of the field. They show strong local testing results. So a local test with a number of queries that only depends on the total degree. For local decoding, they actually show that the picture is more complex. If the field has small characteristic, then they do have a local decoding procedure. For large characteristics or over the reals, the codes aren't locally decodable. So arguably, this is the first natural separation between a code that's locally testable but not decodable. And hopefully we'll hear about these very nice new proof techniques, because previously known proof techniques fail in this setting. The third paper, Proofs of Proximity for Distribution Testing by Chiesa and Gore, now talks about testing not on codes, but for distributions. And this is a question that's been receiving a lot of attention recently, given samples from a distribution, trying to determine whether it has a certain property or is far from having that property. Sometimes it's easy, sometimes it's hard, and in this paper, the authors ask whether having access to an all-powerful prover can help. If we only want to verify, so we have a proof, and given samples from the distribution, we want to verify whether it's close to having the property. And we can talk about non-interactive Merlin-Arthur proofs or even interactive proofs. And the paper gives a detailed study of this landscape. They show that it's fundamentally different from what was known for testing general objects given query access to the object. So usually we have query access to an object in local testing. With distributions, we have sort of random access. We can access random samples from the object, and that leads to a completely different landscape. For example, they show that many rounds of public coin interaction can't give you more than a quadratic saving over what you could do without a prover. Finally, the last paper talks about efficient testing of graph properties without efficient regularity by Shapira and Gishboliner. They study the problem of subgraph freeness, testing subgraph freeness, whether a graph has a certain subgraph or not. Central celebrated question in the property testing literature. Often proofs are given through variants of the Semeretti regularity lemma, and the unfortunate consequence of that is that it yields, we get lots of general results, but the complexity has a very high dependence on the proximity parameter. In particular, it's a tower of exponentials. And the big question is, can we in general avoid these towers? And this paper shows for a particular problem for induced four-cycle freeness. They give a tester with complexity that is less than the tower, so they sort of beat what you would get by using the regularity lemma. So very promising for addressing, a very promising step towards addressing the general question. In particular, now we know that for questions of this type, for this type of property testing question, we're not stuck with the regularity lemma. We can do better. So a beautiful result in its own right, and hopefully the first step towards getting general results with polynomial dependence.